Get under me, kids!
Where's Nema?
I don't know. I saw her earlier today in Blier's class.
There's Professor Sherman, maybe he'll know.
Good morning, class.
Hey, what's up, P. Sherman?
Professor Sherman, where's Nema?
After seeing those horrible test scores, I decided you all needed some more motivation. So I've hidden Nema. In order to find her, you must go on a journey. On each stop along the way, there will be related rates or optimization problems. You must answer the problem correctly in order to unlock a clue. Here's the first problem.
The problem says, find the dimensions of a rectangle with an area of 1,000 meters squared whose perimeter is as small as possible. To start out the problem, we draw a picture of the rectangle with x as the height and y as the width. We then minimize the perimeter equation. We also need to find a constraint in order to make the equation with one variable. The constraint is 1,000 equals x times y, so it becomes 1,000 over x equals y. We plug the constraint into the perimeter equation. Once the constraint is plugged in, we take the derivative of the equation, which is p prime equals 2 minus 2,000 times x to the negative 2. Then we set the top equal to 0 to find the zeros of the equation. We find x equals square root of 1,000. We then check to make sure it is a minimum by plugging a larger and a smaller number into the constraint. We find it is a minimum, so we plug square root of 1,000 in for x, and we get y equals square root of 1,000. Since we know it is a square, we know the dimensions are square root 1,000 by square root 1,000.
Good job. Here's your first clue. From now on, every time you get the right answer, the new clue will magically appear. But you better hurry, or my niece will have a new clownfish.
Oh my god, what does it say? What does it say?
This is where students learn about us and where we live.
Wow, I
I
wonder where
think
that
that's
could be.
Mrs. Brown's fish tank.
Okay, let's go.
You guys sure? I'm not sure. Where am I right now?
There's the fish tank in the problem.
Oh.
The problem says, a school of herringfish is swimming north at a rate of 10 miles per hour. A bull shark is swimming east at a rate of 12 miles per hour. They are swimming towards the same point. If the school of fish is 100 feet away from the common point, and the bull shark is 200 feet away from the common point, what is the rate of change of the distance between them?
Oh, I think I know how to do that. Let's see what we remember. Related rates problems find the rate of change of something in relation to the rate of change of something else. Let's go through the steps. First, draw a picture that shows what you know and what you are looking for. In this picture, x represents 200 feet, or the distance the bull shark is away from the common point. Y represents 100 feet, or the distance the school of fish is away from the common point. H is the unknown distance between them. Using Pythagorean theorem, h is found to be 223.607 feet. Next, write down the known rates of change. dx over dt, or the rate of change of x, is negative 12 miles per hour. This is negative because x is getting smaller as it approaches the common point. dy over dt, or the rate of change of y, is negative 10 miles per hour. dh over dt is the rate of change of h, or the rate of change of the distance between the bull shark and the school of fish. This is what we are looking for. Now we differentiate both sides of the Pythagorean theorem equation with respect to time. This will include x, y, h, as well as dx over dt, dy over dt, and dh over dt. The derivative of x squared is 2x dx over dt. The derivative of y squared is 2y dy over dt. And the derivative of h squared is 2h dh over dt. This gives us the equation 2x dx over dt plus 2y dy over dt equals 2h dh over dt. After this, we plug in our distances and rates of change. X is 200, dx over dt is negative 12, y is 100, dy over dt is negative 10, and h is 223.607. We can now solve for dh over dt. Negative 4,800 minus 2,000 equals 446.414 dh over dt. Divide both sides by 446.414, and we find dh over dt to be negative 15.232 miles per hour. Therefore, the distance between the school of fish and the bull shark is changing at a rate of negative 15.232 miles per hour.
Good job.
Thanks.
Oh, look, there's the clue.
Where do fish go when they need nutrients?
That's gotta be the cafeteria.
Guys, where's Dory?
Oh, I think she got lost on the way here.
We have to go find her on the way to cafeteria.
Okay, let's go.
Boy, sure is clear up here. Hey, little guy. Call him Squishy, and he shall be mine, and he shall be my Squishy. Come here, Squishy. Come here, little Squishy.
Look, there's Dory.
Hey, Dory, come on, let's go to the cafeteria. We're going to our next problem.
Who are you? Alright.
Oh yeah, you guys are.
I'm in my math class. I forgot about that.
Oh look, there's the problem.
Pass it.
Oh, this is another related rates problem. Alright, so this problem says that the 8-foot diameter of a spherical methane gas bubble is increasing at 2 feet per hour, and the 12-foot long edges of a cube of sequestration netting containing the bubble are increasing at 3 feet per hour. Is the volume contained between the spherical gas bubble and the cube of netting increasing or decreasing? At what rate?
The volume between is equal to the volume of the cube minus the volume of the sphere. Let's work with the sphere first. The volume of a sphere is equal to 4/3 pi radius cubed. With a diameter of 8, the sphere has a radius of 4 feet. If the diameter is increasing at a rate of 2 feet per hour, the radius is increasing at a rate of 1 foot per hour. Now we find the derivative of the volume equation. The rate of change of the volume is equal to 4 pi radius squared times the rate of change of the radius. Now we plug in our numbers. The radius equals 4 and the rate of change of the radius is 1. We find the rate of change of the volume to be equal to 64 pi feet cubed per hour. Now let's find the rate of change of the cube. The volume of a cube is equal to x cubed, and the sides of this cube are 12 feet long. We know that the sides are changing at a rate of 3 feet per hour. Now find the derivative of the volume equation. It is the rate of change of the volume is equal to 3x squared times the rate of change of the sides. We plug in our numbers and find that the volume of the cube is changing at a rate of 1,296 feet per hour. We subtract the rate of change from the volume of the sphere from the rate of change of the volume of the cube and find it to be a positive number. Therefore, the volume between is increasing, and it is increasing at a rate of 1,094.938 feet cubed per hour.
Great job.
Whoosh!
There's the clue, guys. It says, this is where we can learn about our fish friends.
That's the library.
Are you sure?
Yes, I'm positive.
I don't know.
Look, there's Nema!
Somewhere beyond the sea, she's there watching for me.
Great job.
Look,
Keep going, keep going. Wait, no.
good job.
Thanks.
Whoosh!
Oh, look, there's the clue.
Where do fish go when they need nutrients?
That's gotta be the cafeteria.